Okay, so we're recording. Alrighty, so here's where we were last time. We were talking about linear approximations. And so recall, the big idea of a linear approximation is we're looking for a degree 1 polynomial, right? I mean, that's the term, linear. I mean, again, not technically linear, but you know what I mean. And we want specifically the one that has the same value and the same first derivative, singular or plural, as the case may be, as the function that we're trying to model. Right? And so we've seen a couple of different versions of this. So on the one hand, this is old news. This is from single variable calculus. This is the unique degree 1 polynomial that shares value and derivative with the original function f at the point A. Okay. All right. And again, there's different points of view on how you can think about where this comes from, etc. But this is the point of view I want to take here. Because it allows us to generalize pretty straightforwardly. I don't need to be able to visualize what the graph of a multivariable function like this looks like to be able to talk about, okay, well, is there a function that agrees in value and in derivatives? Now, there's several first order partials that I would want to agree, right? But nevertheless, this is kind of a multivariable ripoff of what we did for linear approximations in single variable, and this is the function that works. As we discussed last time, and we can rewrite it like this using this notation here to represent the gradient vector. Okay, again, all discussed last time. Hope everybody remembers this. We all good? Okay. And then where we kind of didn't really quite have a chance to really finish last time was talking about the vector-valued multivariable case. The previous was only real valued, right? Now we've got to consider vector valued. And we want to find, again, a function that agrees in value and all of the various partial derivatives. And keep in mind, I've got several different input variables, x1 through xj, with respect to which I could take partial derivatives. And I also have several output components, f1 through fm, of which I could want to take those partials. So I need it's not just a list of partial derivatives that I want to agree, it's an entire array of partial derivatives that I want to agree. Sort of a 2-index collection of partial derivatives. So again, I want, just to say it briefly though, I want L to look just like F in terms of all of its partials. Right? That's ultimately all that's saying. Okay. Right, and here's the answer. And this is about where we ran out of time last time. Notice again, I am just for notational convenience using this here to represent this matrix of all the partials of F. We're going to discover today some really neat things about this matrix. For the moment, it's a notational convenience that prevents us from having to write out just a huge, massive list of terms here. Okay? But just notational convenience. And I think this is where we left off. And because I can't remember if I noted the following, let me do it again. Make sure not to accidentally transpose this matrix. It's really easy to do. It's really easy to accidentally do this move, right? So it's very important that the columns correspond to individual input variables that you're taking partials with respect to, and the rows need to correspond to individual output components that you're taking the partials of. And again, it's got to be this way. Given the conventions of linear algebra and how you multiply matrices and stuff, this is not optional. It's got to be this way. So heads up and be careful for that. Okay, so a quick example, which I don't think we did last time. Maybe we did. Did we do this example? No. Okay. All right. And this is very plug and chug. I in some sense have the answer right there. This is how you do a linear approximation. We're just going to write down the formula and do what it says. So there's our formula. I just need to know, well, for one thing, what is the value of f of a? Well, here's f. here's the a that I'm going to plug into it, and the value of the function becomes those numbers right there. That's just arithmetic. Right? Okay. Now, there's the derivative matrix. What do I do with this derivative matrix? Well, the derivative matrix is all the partial derivatives. Notice what I have here. These are all of the partials with respect to x. First column, partials with respect to the first input variable. Now you got to go through and check. Right? 2x, y, 6xy cubed. Right, there we go. Everybody good? Okay. Likewise for the second column. Second column corresponds to the second input variable. Okay. Again, though, I'm going to be plugging in this point, so that plugs into there. And the matrix turns into this. And again, it's just plugging in arithmetic. So nothing really exciting there. And then lastly, last part of the equation, well, multiply that matrix times the x minus a vector. And, this is the x vector. And, as previously noted, that 1, 2 is the a vector. And so, boom, there you go. Now, I suppose you could multiply this out, but, again, what's really the advantage there? Unless you are really needing to actually simplify it for maximum computational convenience. Yeah, sure, go ahead, multiply it out. But I honestly mostly just leave it like this most of the time, yeah.
If it gives us on the test, we leave it like that.
Unless it specifies otherwise, yeah, I can't. I mean, there's a tendency for people to think that multiplying things out is intrinsically simplifying. I don't think that's all clear. Right? So when you multiply things out, you also lose information about how to factor it, for example. Right? And here, I think there's a lot of neat information encoded in how this, I'll say, loosely speaking, factors. Right? So I think I'd prefer not to multiply it out. Yeah. Okay. A couple of really quick observations. I don't want to spend a lot of time on this, but you'll just notice if you look at the derivative. Excuse me, I should be careful what I call this. The matrix of partial derivatives that we've created for notational convenience only at this point, and about which we know nothing else for the next, 5 minutes, 10 minutes. This matrix, if you look at one of the rows, that row, we've already observed that the individual elements are all partials with respect to x1. And now I'm just going to make the observation, well, that makes the row itself the partial of the f vector with respect to x1. So it's just, just an observation. The other thing I'll point out, and this one we have not previously noted, if you look at a row instead of a column, that row, there's something really interesting about it. Let's come back up here to our general formula. What can I say about this row? Well, we've already observed, we're taking partials of f1 everywhere in that row. That means that this is, in fact, all of the partials of that function f1. All of the partials of that function, all the partials of that. Where have we heard that phrase before? All the partials of a function. That's the gradient. It's the vector that is all of the partials of that function. Right? So, again, there it is. How about that? Neat observation. Rows of this matrix are the gradients of the component functions. So, neat fact. Useful sometimes. And I've already talked about this. Technically L, we call it the linear approximation. Technically, it's not linear because it's just not a linear transformation. 0 doesn't go to 0, for example, right? It's just not linear. But as to why they call it linear, the part of this formula that's doing most of the work, you might say, in other words, other than this constant right here, the part that's doing most of the work is this matrix. And you will recall that matrices are all linear. So this is an approximation, most of the work of which is being done by a linear term. term. So thus the term linear transformation, and linear approximation. Thus the term linear approximation. Just because of that. Okay. Slight abuse, very common. Okay, so what's a tangent plane? And I'm going to segue into that by talking about tangent lines. And again, there's different ways that you can approach this. And I'm just going to give you the point of view that I like. We've already established that this is the formula for this thing called the linear approximation. It's a function. Linear approximations are functions. It's an algebraic thing, right? Okay, there is this thing called the tangent line. That you kind of want to say that the tangent line kind of also, it feels like it's approximating the function, right? The difference is, well, no, it's just a geometric thing. It's a geometric representation of the function that's actually approximating f, right? So you might say that this curve kind of tracks or mimics maybe, follows perhaps the graph of f, but technically anyway, this is a curve and it's not approximating anything. Right? So the relationship to be aware of is that the tangent line is the graph. Tangent line specifically is the graph of the linear approximation. All right, so now innocent observation, you might say. Hope all of this looks familiar. And again, I know high schools aren't as particular as I am about the use of the word graph. But anyway, I hope this all looks relatable. So that said, we can make the exact same observations about tangent planes that we did about tangent lines. It's the same exact relationship. We have a pre-existing formula for linear approximations. Right? There's our linear approximation. Its graph is what we call the tangent plane now, not the tangent line. I know it's a plane because you can look at the formula, right? This graph that is this tangent whatever, this is a graph of a function of two variables. That's not going to be a curve, it's going to be a surface. So being linear, this is a tangent plane. What do you think? Everybody okay? All right. Okay, just a little lingo. Okay, so on to differentiability. I kind of skipped over an important bit at the very beginning of linear approximations. It was deliberate. And that is, you see I got it in big box here, if it exists, right? So this analysis down here kind of assumes that the linear approximation exists in the first place, right? I write this down kind of on the assumption that everything's going to work out and that, partial derivatives I can compute, and there's just, everything is as nice as I kind of want it to be, right? We have to recognize it is possible that our function here might be some sort of severely nasty, ugly, weird thing that does not have a tangent plane. And if this function, does not have a linear approximation, If this function does not have a linear approximation, then a generic formula isn't going to work, right? This is just it just doesn't make any sense at all. So all of this analysis that we did here was on the assumption that the linear approximation exists, and now we have to entertain the much harder question: yeah, but does it? And the much discussion ensues. Yeah, question.
Would you mind explaining the tangent plane again?
Yeah, sure. So the idea of the tangent plane is the same as with a tangent line. You okay with the idea of a tangent line being the graph, right? So we're going to do the same thing over here. Again, we're looking at a graph. It's just that now we're looking at a graph of a function. It's not a function of one variable anymore. Now it's a function of two variables, right? And so this graph, instead of here you have a graph of a function of one variable, it's going to be a one-dimensional thing. It's a line. Here we're looking at a graph of a function of two variables, and it's going to be a two-dimensional thing. And that's a plane, as it turns.
Each point will have like a different plane.
Each point will have its own tangent plane. That's right. In the same sense that in single variable calculus, every point has its own tangent line. Absolutely. Yeah. I saw another hand somewhere. Yes?
I just wanted like another clarifying question.
Yep.
So the tangent plane is like the plane for the tangent lines in all of the directions at a certain point.
Yeah, I mean, you can think of it that way. Yeah. I think it's simpler to say it's the graph of the linear approximation, right? But now to say it your way, yeah, you can say, okay, at this point, look first in that direction, see what the tangent line looks like, that gives you this, and then look maybe in this direction, and look what the tangent line looks like there, maybe it looks like that, and then you could keep doing that for all different directions through here. And that would give you, a bunch of lines. All of those lines together, all of those tangent lines together would make the tangent plane. That's true. If the function has a tangent plane, to bring it back to where we were before. But yes, that's a true fact. But again, I think also a little bit harder way to think about it. Yeah. Okay. All right. Okay. So does a given function have a what you might call a reasonably acceptable linear approximation? Now you'll notice that I've got this in a section on differentiability. So these end up being really the same question. If there is a good linear approximation, we're going to say the function's differentiable. If the function's differentiable, that we can conclude that there is a good linear approximation. They're really kind of the same statement. Here's the unfortunate fact. I don't know, unfortunate for me, maybe fortunate for y'all. This is actually a really deep question. And there's a lot to say about it, and it's really beautiful math, and I wish we had time for it, and we don't. So I think it's stuff that you should be at least loosely exposed to. So I'm going to go through this discussion about differentiability and the existence of linear approximations somewhat quickly, and with the understanding that I really don't know how to write a good Math 219 test question about about the existence of linear approximations and the strict condition of differentiability. So the next 2 pages of discussion, you're kind of excused in the sense. I mean, I want you to hear it because I think it's important that you know approximately what's going on and approximately what this means. But you're excused in the sense that, yeah, I don't see any test questions coming out of the next 2 pages. So again, just the next 2 pages. Okay, so let's start with this function right here. Defined by that weird little, I hesitate to call that a formula. So it's a rule, right? Rule of assignment, but not exactly algebra. And notice the value of the function is 1 if you're looking directly above one of the axes, and the value of the function is 0 everywhere else. And so, like, over here the function is 0, and over here the function is 0, and over there the function is 0, and over here the function. So everywhere except above the coordinate axes, the value of the function is 0. Above the x and y axes, the value of the function is 1. What an odd little function. Is this function differentiable? Well, we don't know what that word means yet. Should this function qualify? As we're defining differentiability, would we like to consider this function differentiable? And I propose, no, come on, the thing's not even continuous. It's got a significant, weird discontinuity at the origin, for example, right, and several other places. But I don't think we should want to call this function differentiable. Here's the problem. At the origin, if you look in the x direction, the function is constant. That partial derivative is defined without any problem. The partial derivative in the x direction is 0. No problem. If you look in the y direction, the function is constant as you move in the y direction. That partial derivative, perfectly well defined, no problem, partial derivative is 0. So, at the origin, this function, the partial derivatives exist. You can take the derivatives and yet this function is not differentiable. And that's the first big thing I want you all to get out of what's the difference between differentiability in multivariable calculus versus single variable. In single variable, differentiability means you can differentiate. And that's it. Just can you compute the derivative? The end of story. If yes, then it's differentiable. No, then it's not differentiable. In multivariable calculus, you just can't do that. It just doesn't work. You get this ridiculous situation. So differentiability is going to be significantly harder to define in a multivariable setting. And again, we're not going to go through all of that, but I do want you to see. I want you to see what the issues are. At least we're going to next say, well, let's look at error. If you have an approximation, that an attempt at forming a linear approximation of your function, reasonable to talk about how far is it off. And doesn't it seem also reasonable that if you want the linear approximation to be a good linear approximation, that we should just want that error to approach 0? And if you think about it, the error is what's bad about the approximation. If the badness goes away, isn't that good? Right? Just to oversimplify, seems like this would be a reasonable choice. And it turns out that it's not. It's more complicated than this as well. And here's my example. Here's a function. Single variable function. Nice, easy example. Here is what you might call a candidate linear approximation. Obviously not a good one. But anyway, let's just try to quantify, does this qualify as a good linear approximation? And the thing is, the error, that difference, that error approaches 0. All that error goes away. You can watch the errors getting smaller and smaller and smaller as you approach your A point there. So does that mean that this is a good linear approximation? No, this is still obviously a terrible linear approximation, right? Obviously the linear approximation should in this case should actually be 5x, not 3x. It's just wrong. So this doesn't work either. Error approaching 0 is not good enough. Everybody see the problem there? All right. Here's what's going to be the winning move. It's not good enough to just look at how far are you off. We want to look at how far are you off. You might say per unit, how far away is your input. So how far away is the output compared to how far away is the input? This is what we call relative error. Because, if you think about it, right? The further away the input is, the more error you would be expecting to get, right? And so relative error is arguably a natural thing you want to look at. Okay, so let's see that old example again. Again, we have this function. Let's try that again. There we go. That function here is our candidate linear approximation that we already know. It really shouldn't qualify. We're looking for an algebraic quantification of the obvious assertion that this stinks. Right? How do I say that algebraically? This stinks. Right? So the way we say that algebraically is to talk about relative error. So not just the error itself, but that divided by that. So there's your relative error. Error divided by, you might say, input difference. Right? And if you punch this up, not hard to do the algebra. Look and see what the limit of that is. The limit of that is 2, which is not 0. And so the relative error does not go away. And this is our algebraic way of indicating that, the relative error here is not small. It's not small enough. It's not approaching 0. This is the algebraic way of saying that this is not a good linear approximation. Everybody see approximately what happened there? Yep.
So the test then is like if x approaches 0 for r of x.
One more time. Say it again.
So like a good approximation then would be if like x approaches 0 for r of x, then it's a good approximation.
So a good approximation would be one where this r, this relative error, actually approaches 0.
Yeah.
Yeah, that's right. If the relative error approaches 0, then we would say that's a good approximation. Right? Okay. All right. So this is actually what I kind of wanted to build up to, is this idea of relative error approaching 0. And very often the way we say approaching 0 is vanishing. So vanishing relative error is where the definition of differentiability comes from. And ultimately that's all this says here. Now that is a page full of complicated looking math. All it is saying is that relative error approaches 0. And then just don't forget, the error is true value minus approximated value. Furthermore, don't forget that, and I'm going to put some parentheses in here temporarily. Don't forget that the approximated value is our linear approximation there. Right? So this great big monstrosity on the right, this is how we tend to write down the definition of differentiability. All it's saying is relative error should approach 0. It's really not that big a deal. That said, it is clunky. It's awkward to deal with. It's not something that I wish we did, but it's not something we have time for at Math 219. And so I'm not going to make you manipulate and deal with any of these things. But if you ever see the definition of differentiability, this is where it comes from. Okay. The last thing I'll point out, and this is just another sort of bit of lingo, it's just another way to think about error. So error that we have there, written here as true value minus approximated value. And I just want to point out that if you take that and kind of move terms around, move parentheses around just a little bit, nothing really happened there. I'm just moving parentheses around. You get this alternative formulation of error as the actual change in the function minus the estimated change of the function. Right? This is a nice way to think about it. We're interested in the function changing and how much the function changed. This is how much it actually changed. This is what our linear estimate was. And both of these are objects of interest. We're going to talk about these, so note the names. The actual change, the elusive, actual change in the value of the function is called the increment, and the estimated change is called the differential. Okay. All right. Okay, so now that was the 2 pages. These are the 2 pages that, again, I don't know how to write a reasonable test question for these. But going on now, I know how to write all sorts of good test questions for the rest of this stuff. So fair game resumes. I want to tell you about something called continuous differentiability. It's a scary sounding thought because differentiability itself was a hard thing to talk about. So hard to talk about I didn't even really tell you. I skimmed the surface at most. Right? This would seem to be a stronger condition, and you would think that in order to check a stronger condition, you would have to do more work, because you'd have to check the differentiability, and then you'd have to furthermore check something else, you would think. And it's just not true. It wonderfully conveniently turns out that continuous differentiability is super easy to check. It's super easy. You just have to take the partial derivatives, confirm that they exist, which, by the way, rings a bell. Let's note, right? We made a big deal at the start of class today. The mere existence of the partial derivatives doesn't tell you much, right? This function here, the partial derivatives exist. The fact that the partial derivatives exist means next to nothing. But if those partial derivatives are also continuous, then your function is continuously differentiable. It's what we call continuously differentiable. It's a very powerful condition. It tells us a huge amount of information about the function. In particular, it tells us that the function is differentiable. So, vast majority of the cases, this is how you're going to confirm that a function's differentiable. you're going to do even more than that. You're going to confirm that it's continuously differentiable, and that allows you to conclude specifically that it's differentiable. Yeah.
Is it if f is continuous or the partials?
The partials are continuous. Yeah. So this is the giveaway is the plural. Yeah, that's right. R. So all of the partials are continuous. That's right. Yep. Okay. Okay, so let me tell you, you use this in practice. Question here, is this function differentiable? On its face, you might say, it's asking about if this is differentiable. Here's the definition of differentiable. It kind of makes it look like you're going to have to deal with this monstrosity. Right? Which you don't want. So, again, that's on its face. The important trick is to remember this theorem here about the continuous differentiability actually implying differentiability, and we proceed as follows. You can take all those partials. By the way, you don't even have to write them down. It's perfectly clear, casual inspection, that this is a polynomial, and all of its partials are also polynomials. So this is almost effortless. All of those polynomials, those being the partials, they exist everywhere. No polynomial is undefined anywhere. And furthermore, they're continuous. All polynomials are continuous everywhere, right? It's just common knowledge. So we've got here a function whose partials are all continuous, and that means by definition that is continuously differentiable. And that means by this theorem up here that I can conclude the function is differentiable as desired. Everybody see how that worked? This is how you do business in practice. If you need to know something's differentiable, please do this. Don't go to the definition. Okay. All right, I do want to... Oh, yeah, go ahead.
Are there functions that are differentiable but not continuous?
Sadly, yes. There are some functions that are differentiable but not continuously differentiable. I'm going to call them anomalous weirdos. And we're not going to have to deal with... is that a fair statement? Let me think about this. Yeah. I don't see any of those coming up in this class. They're rare. Yeah. They're oddities. Yes.
So for the partial derivative to exist, doesn't the function itself also have to be continuous? Meaning both?
Yes,
okay.
That's absolutely true. Yeah, and I'm going to get to a related point in just a quick moment. There's a good observation. Absolutely true. All right. Okay, so one more point about this I want to emphasize. Y'all recall, and I've talked about this in that recording before class started, and I've said it a few times here in class. But this is a class about ideas. It's not a class about answers, right? And so you have to show your work. You have to explain your reasoning. And in particular, you need to document all of the important points of the reasoning, right? And I think this is a really lovely example of there being important points that a lot of students would kind of gloss over, not really thinking through how important it was. So, for example, a student might write, to this question... A student might write, all the polynomials are partials, and therefore this is differentiable. Now this is a true statement, and this is a true statement, but there's a big gap of reasoning, right? It was really important that those partials be continuous. The fact that they are continuous, that is what allows you to conclude continuous differentiability. That's a huge point, right? Minus the continuity, you've got nothing, right? Per that example several pages back. So the continuity is important here. This is a very important sort of part of the actual reasoning being done. So you've got to document that. Does that make sense to everybody? Right. And then likewise, okay, so now you know the function's continuously differentiable. You got to note that it's continuously differentiable. Oh, a bad color choice. That it's continuously differentiable, and that the continuous differentiability is what allows you to conclude the differentiability. So again, a lot of students would write partials or polynomials, and maybe they might even write and they're continuous, and therefore we have differentiable. Well, therefore we have continuously differentiable. And again, important theorem, powerful theorem that allows us to go from here to differentiability. So, easy to forget to write in the continuity, easy to overlook the importance of noting the continuous differentiability. And you'd need to again, document all these important parts of the reasoning to get full credit. So I hope that makes sense to everybody. I just want to make sure everybody's fully notified of what's going to be required. Okay, all right. And again, this is just again documenting the important parts of the reasoning. Okay, so somebody asked a question about continuity, and here is a true fact: every differentiable function is continuous. Proving this is a little heavier than we can do in Math 219. It's more of a Math 431 thing. It's not that big a deal, frankly, but it's just we don't have time. But anyway, true fact. Every differentiable function is continuous. In practice, the more useful version of this is what we call the contrapositive. Hope you all remember the contrapositive. The contrapositive of P implies Q is not Q implies not P. Case in point being this. And I think if you think about it, right, it really makes sense. Contrapositives are morally equivalent statements to the original. So this is the version that we're actually going to use most of the time. So we have an easily observed condition that will allow us to conclude something about the possibility of differentiability. And so, for example, let's look at this example that we had previously. This ugly function here, considering at the origin, what's going on at the origin there. Well, it's clearly discontinuous, and discontinuous implies not differentiable. Game over. And I don't have to take partials or anything. It's we've got a discontinuity, and therefore it's not differentiable. One step. Pretty good? Okay. All right. Okay. So, quick reminder. Linear approximation. Note I've put in my appropriate disclaimer now. This is we're going to assume that we have a differentiable function. Keep in mind what differentiable means. There's a definition and everything, but the motivation of differentiable is that the linear approximation is doing a good job. That it is in fact reasonably described as a linear approximation. It's not just some random linear function. It succeeds to at least a certain level of acceptability in terms of how well it's approximating the function. Okay, that's what differentiable means. Okay, so that said, recall a requirement is that the linear approximation have the right value at the point in question. And then further note, I can take this term and kind of toss it over to the other side of the equation like so with a minus sign. Hardly anything happened, right? And now, check it out though, we have a pretty interesting way to write down this equation. We have our output differential directly related to our input differential. Right? That how much did I change the input? What's my corresponding linear estimate of the change in the output? Directly related by this thing that I've previously made a point of, tried to make a point of describing awkwardly as, well, it's this notational shorthand in which we stick all the partial derivatives in a certain way so that the linear approximation works out. This thing, this awkwardly referred to thing, relates input changes to output changes. That's our cornerstone point of view on what a derivative is. It's something that relates input changes and output changes. This thing does it. This is what we call the derivative. So it's not just a notational shorthand. It's not just, I don't like writing out all those terms. I'm just going to kind of compactify. I'm going to make everything a little bit more efficient. This is of very important mathematical significance in that it is literally the derivative. It's the thing that relates input changes and output changes. Everybody see that? Pretty neat observation. You can rewrite that as I have it down here. The input differential dx, the output differential df, and this matrix relates df and dx. So again, the derivative. So here's kind of a picture of that. Oh, a little bit of terminology. So we call it the derivative. Sometimes we call it the derivative matrix because it's a matrix. Sometimes we call it the derivative transformation. Recall that all matrices, such as this is, all matrices are linear transformations. So this is the linear transformation that relates input changes and output changes. So the term derivative transformation also really makes sense. Then somebody asked at some point, it might have been in the other class, but sometimes this is called the Jacobian Matrix, and with that in mind, sometimes written with a J instead of a D. Suit yourself. I don't have strong feelings on that. Okay. All right. So keep in mind what we've got here. We've got a function that takes input points to output points. Right, and f takes a as its input and gives you f of a as its output. Well, you could imagine that endpoint might displace by some amount, and that correspondingly we would have our linear approximation estimate of how much the output would change as a result. And the thing that relates the input change to the output change is df, that matrix of partial derivatives. That I'll always refer to in the future as the derivative or the derivative matrix. What do you think? Anybody see? Okay, there is something a little bit undesirable about this particular point of view. The input change is clear. I was here, now I'm there. Right? The output differential, there's something a little bit awkward about this. My output value was here. Now my output value, it's not actually here at the end of this arrow. It's somewhere near there, and near in the sense that vanishing relative error. Right? So that doesn't exactly roll off the tongue very nicely. So something a little uncomfortable. I like to get rid of that issue by thinking of the changes not as being discrete changes, but as being rates of change, aka velocities. And all you got to do is take this equation, divide by dt, there and there, right? Just by dividing by dt, notice that now what we have is an input, not a change, but an input velocity, an output, not a change, but an output velocity. These are instantaneous velocities. The limit, as it were, let h approach 0 is kind of already wrapped up in the side of the fact that these are instantaneous velocities. And so I don't have to talk about approximations anymore. df literally takes that input velocity exactly to that output velocity. No discussion of approximations needed. So this is, again, it all comes about by this little fast one, divide by dt, interpret as velocities. Take a limit as t approaches 0, however you want to say it. And we get I think, a little bit more satisfying, rolls off the tongue better interpretation of df. It relates input velocities to output velocities. Everybody with me? Okay, so real quick, you could do something analogous with the gradient. Recall that we used the gradient for real valued multivariable functions, and that's fine. You can do that, and you get down to this same thing. Okay, the gradient can be interpreted as the thing that relates input changes to output changes. If you prefer, divide by dt. It's the thing that relates input velocities to output velocities. Fine. So, question, how come it's the gradient for real valued functions, but it's this matrix for vector valued functions? And the answer is they're actually the same. So, in fact, if you were to take this case here, this real valued case, notice that instead of writing the gradient and doing a dot product, you could instead take the derivative matrix. Now, this is real valued, so there's only one row. There's only one component of output to take partials of. So you only get one row. It's a row consisting of all the partials of f, just like this is a vector consisting of all the partials of f. It's all the same stuff, just kind of assembled, you might say, a little bit differently. So instead of viewing this as a vector and dotting it, you can view it as a matrix and matrix multiply. Let's see, we don't put anything in there, but you know what I mean. The matrix multiplication. And, of course, it's exactly the same thing. It's exactly the same arithmetic. So this is not a different formula. This is just an alternative form for the same formula. But again, this only works for real valued, right? Gradient only is a thing for real valued functions. So it's sort of a one case where you have this alternative form. Okay. All right. Okay. Everybody with me? Everybody happy? Okay. So a couple of quickie observations. We've talked about the derivative being a matrix. Matrices take vectors to vectors. All matrices are linear. Recall that from first day of class as a flashback from Math 218, of course. Here's the thing. DF is a matrix. Yeah, fine. But D by itself, what is D? Let's think about this D thing by itself. D apparently is something we do to a function, right? So the input is a function, and what do you get when you do D to a function? Well, you get DF, which is it's a matrix. Right, so I guess let me fill this in as blue. So D, aka the act of differentiation. Sometimes we call this the differentiation operator or the derivative operator. Is a weird kind of a function that takes inputs from this vector space and returns elements of this vector space. And so it's a significant observation to note that the act of differentiation, D itself, is also linear. So it's, again, a very different state. We're not talking about DF. DF is a matrix. Of course it's linear. We're talking here about D, the act of differentiation, the act of turning a function into a matrix. This process here is linear. And again, in the sense that if you put a linear combination in, you get a linear combination out. And you can see an example of this in action, and this is straight computation. There's no tricky curves on this. Here's a function in its derivative matrix. Make sure you can compute that. Confirm. Here's another function in its derivative matrix. Be careful with this one. Again, you got to make sure that you don't accidentally transpose there. You can't. You got to make sure to get the rows as the rows need to be rows. The columns need to be columns. It's easy to accidentally get that wrong. And you can talk about taking a linear combination of those, in which case you get this function that has that derivative. And good news, everything fits. You can look at this combination of the derivatives. You can look at the derivative of the combination, and same thing. And again, it's just a matter of checking the arithmetic. Take multiply this out, confirm that it's the same as that. And so we have linearity, at least in this example, we have an example of the linearity of the D operator. Okay, super quick. There's various forms of product rules and quotient rules. Y'all can look in the book for these. It's pretty straightforward, and they're direct computation to confirm that they work. So give those a look, make sure that you're aware of them, and we'll draw the line right here for today, and we'll pick up with higher order partials on Monday. Y'all have a good weekend. See you later.